And this is going to lead to a sea change in statistical mechanics. So here's this great quote from Maxwell. The true logic of this world is the calculus of probabilities, which takes account of the magnitude of the probability. Now, I said it's a sea change. Now, the natural metric, which is just actually defining distances in shape space, this is all that remains of kinetic energy. Kinetic energy just goes out of the statistical mechanics of the universe if this picture is right. And what instead in its place you get is it defines the measure for the probability of shapes. And you'll see this in a very dramatic form. And this is going to be the probability, the calculus, which takes account of the magnitude of the probability. It is a gift of shape space. You take out scale and you're given perfect, rigorous probability measure. And you can do that because shape space is compact. You've got something which tells, so you can give it a nominal volume. You can then say, what is the ratio of the size, the volume of a region within shape space compared with the total. And even more interesting is that we see, we're going to foliate shape space by the values of the shape of the complexity, the shape complexity, and the same will hold there. The shape complexity, it's multidimensional. Well, it's one-dimensional in the three-body problem. It's those contour lines there. And the shape potential, the measure in that on the shape sphere is just the length along the contour. That is the measure. And I don't think you can ask for anything which is more rigorous than that. There's no coarse graining, no fishy saying it's a confined system and you're not sure how long it's going to stay confined or anything there. So that's the magnitude of the probability which Maxwell says we need. And that's the measure. We've got it there. So there's going to be a primary state function, and that's going to be the shape complexity. And then a second one we'll come to is going to be a Shannon entropy of the shapes. I'll come to that. That will require some coarse graining. I think it's possible maybe one can do it without coarse graining, but already with coarse graining, it's going to be interesting. So now, the extrema of the complexity or the shape potential are extraordinarily interesting. Just make a note of the three references that I put there. There's a wonderful paper by Donald Sari who talks, I'll tell you in a moment what central configurations are, but he quotes the mathematician Stephen Smale saying that the study of central configurations is a problem for the 21st century. I hope you'll agree with me by the time I finish this talk. There are two lovely papers. One is by Richard Batty, Gary Gibbons, and Paul Sutcliffe, and another by George Ellis and Gary Gibbons, which I strongly recommend to read. Now, a central configuration, its significance was recognized in the late 19th century. It's a configuration in which the force that every particle in the system acts on each individual particle is such that that force is directed towards the center of mass, and the strength of the force grows the further the particle is away from the center of mass. So if the particles start off in a central configuration at rest, they will fall without the shape changing until they all collide in an instant at the center of mass. And that's called a total explosion. And people started studying these things in the 19th century. Now that example I gave where the shape does not change, that's a homothetic total collision. Vastly more interesting are Newtonian, highly non-trivial Newtonian n-body solutions in which the shape does change until they actually get to the shape which is a central configuration, which satisfies where the shape satisfies that condition, and then they collide at that point. And N-body specialists have not found any way to continue the motion beyond such a total collision. So that's the end of the story, going at it that way. Now, in 2 dimensions, instead of them falling to rest, you can have what's called balanced motion, where if the system is rotating, the centrifugal force balances the gravitational force. And Euler was the first person who realized this with the collinear Euler configurations. And he pointed out that if the moon was 3 times further from the Earth than it currently is, and it was on a line Sun, Earth, Moon, we would see the moon full forever. It would stay there forever. And then Lagrange discovered the same sort of property with the equilateral triangle, which is at the absolute minimum of the shape potential. Then I don't know whether he thought about it, but certainly it was realized, somebody realized that there ought to be asteroids forming equilateral triangles with the Sun, Earth, and this asteroid going around on the Earth's orbit. And indeed, they were looked for and they were found on both ahead of the Earth and behind the Earth in its orbit. These are the Trojan asteroids. So this was, a great discovery there. So now these, under the James Webb Telescope, is now sitting at one which is at a Lagrange point with the Earth and the Moon. So, it's right at the heart of Newtonian gravity. Now, these central configurations, there's an incredible number of them. Basically, they're at least n factorial. And they have the absolutely beautiful, and at least one of them, and maybe a unique one, if the masses are all unequal, then I think I'm virtually certain, unless it was a great fluke, there will be one shape which has the absolute minimum. And it's a beautiful consequence of Newton's potential theorem, the famous one that Newton was so proud about, that when you have lots of particles and the complexity is low, they form an almost perfect uniform sphere. And this is the calculation, numerical calculation in the paper by Batty, Gibbons, and Sutcliffe. It's just incredible. That's Newton for you. And so there's a slice through it shown on the right there. So the equilateral triangle, by the way, the equilateral triangle is the smallest mathematical universe because all the sides are equal. By my internal measurement, it's the smallest universe. The regular tetrahedron is also has that property of having the absolute minimum of the complexity. So now you can, because you can reverse the time, a total collision is also a total explosion. It's a Newtonian Big Bang. They come out of what seems to be a zero size, but if size it isn't kosher in shape dynamics, you mustn't think about size, you must think about shape. So actually it starts with a very uniform shape, and then the shape just gets more structured and clusters form, Kepler pairs form, and so forth there. Now this nature of total collisions and total explosions is very special. And this is where you see again that the shape potential, the scale invariant form of the Newtonian potential is decisive, because it's very interesting. In the three-body problem, if the masses are not all equal, then the shape potential has the Hessian is what determines it. So if the Hessian has the largest eigenvalue, and it will if the masses are all unequal, virtually all these solutions will either come in or go out along that one there. And if however many particles there are, as long as there's one with a maximum eigenvalue, the great bulk of them go out there, and then they splay out as you see there. So this is, again, shape is everything. It really is, if we're talking about modeling the universe. Now, even more interesting, so a total collision can only happen if the angular momentum is zero. Even more interesting is what's called parabolic escape. This is where the particles all manage to escape to infinity from some general initial condition, if it's a very special one. And when they get there, they are in the shape of a central configuration and all the particles have come to rest. And that is only possible if both the angular momentum and the energy are exactly zero. So those are very, very special solutions. And when you take the time reverse of them in shape space, you just have a curve in shape space, which goes from a central configuration out into shape space somewhere and wanders off through shape space. But it starts at that very special point. And this is going to be very important in my argument in a moment. So now the question is, are there any Newtonian solutions which are completely free of Newton's absolutes? And I said this great problem was that if you just plot the Newtonian solutions in shape space, you've got this one extra degree of freedom. I call it the anomaly or the creation measure, because it's the thing that is causing all the structure to be formed, this one extra number. And that really reflects the fact that in Newtonian theory, you have a ratio of overall kinetic energy and overall expansion divided by the amount of change of shape. But now there's some very interesting, so I'm going to say, let us assume that there is a central configuration that has the absolute minimum of the shape potential. Let me call it alpha for rather obvious reasons. And a good Leibnizian like Simon and myself will say the principle of sufficient reason suggests, well, we call it alpha, and then what's going to happen if we say we're only interested in the solutions that come out of alpha or go into alpha? Now, given the curve in shape space, you can reconstruct the Newtonian solution that generated it, that you projected it to shape space. Now, when you actually do that with a parabolic escape solution, and you look at the point where it starts and you say, what is the value of the Newton's size there, the moment of inertia? How large is the moment of inertia at that point, alpha, which corresponds, if you see it as a parabolic escape, there the size is infinitely great. If you see it as a total explosion, which in shape space is indistinguishable, we're pretty certain about that. We're pretty certain it's indistinguishable. The size is absolutely zero. So my conjecture is that the solutions that come in to or come out of alpha, they are governed by Newton's equations. They're governed by the Newton potential. They create all that wonderful structure that Newton does, but they don't carry the original sin of Newton's absolutes. That's my conjecture. And there's an extraordinarily interesting set of such solutions, which I'll come to in a moment.